This is 8.2, testing the difference between means with small samples. So just like we had last chapter, we started with large samples where n was bigger than 30, so we use the z. If our n is smaller than 30, we have smaller samples, we're going to use the t. The two-sample t-test for the difference between means. If the sample size is less than 30, samples are randomly selected and they have a normal distribution, you can use the t-test. The standard error and the degree of freedom will depend on whether the population variances are equal or not. So we're still dealing with the same criteria. They have to be random, they have to be independent, they have to be normal, and our standard error equation and our degree of freedom is going to change. So we're going to have two different circumstances here. So let's split this up into two. Actually, let's do this first. We can write the t equation up top. So again, looks very similar to the z equation. But we are going to have two different situations. So the first one would be if our variances are equal, and then the next one would be our variances are not equal. So the first one, if the variances are equal, we would start out with a pooled estimate for our standard deviation, where this is our equation. And our standard error equation would be here. So again, this is the denominator for the equation we have up top. It would be our pooled estimate times 1 over n1 plus 1 over n2. And our degree of freedom would not just be n minus 1, because we are dealing with two different n's. We would actually add up both of the n's and subtract 2. Now if our variances are not equal, we have a much simpler case where our standard error equation is very simple. We don't have to solve for the pool estimate first. And our degree of freedom is going to be whichever is smaller, n1 minus 1 or n2 minus 1. So again, two situations. You're plugging both of them in to this top equation, and we're using t because our n is smaller than 30. If our variances are equal, we first find the pool estimate, plug it into our standard error. If our variances are not equal, we can go straight to the standard error and plug it back into our t. So if you're unsure what to use, page 443 has one of those charts. It says, is your n bigger than or equal to 30? If you're answering yes, you're going to use the z. If the answer is no, is your population normal? If it's not normal, you can't use anything. But if the answer is yes, you're looking to see if the standard deviations are known. If it's yes, you can use your z. If it's no, are your variances equal? Then you're going to plug it in to the first equations we had on the left side. If the answer is no, you're going to plug it into the second set of equations we had on the right side, which we won't write those down again, but these would be the first and these would be the second. So let's try one of each, one where they're equal and one where they are not equal. This is on page 444. The results of a state math test for random samples of students taught by 2 different teachers at the same school are shown at the left. Can you conclude that there is a difference in the mean math test scores for the students of the 2 teachers? Okay, so first of all, you can't pair these up because the students have different teachers. They're not related. So this is something that's independent. I noticed that my n for teacher 1 is 8 and my n for teacher 2 is 18. Therefore, I have to use my t equation. So let's write our h sub o and our h sub a first. Again, we're talking about whether they are different or not. And the claim is that there is a difference, which would mean they're not equal. Okay. Because the variances are not equal, so if I look at the numbers that they give me, one is 39.7, the other is 24.5. So since they're not equal, and the sample size is 8 for one and 18 for the other, I have to use the one that is smaller. So my degree of freedom is going to be whatever's smaller, either 8 minus 1 or 18 minus 1. Obviously that's 8 minus 1, which is 7. My level of significance they give me is 0.10. So now I'm going to look at the t-chart. I see I'm looking for something that's two-tailed. So I'm going to look at the two-tail column. I'm going to look at the degree of freedom of 7 and the level of significance of 0.1. I see negative 1.895 and positive 1.895. So now that I have my equation, or my rejection region, sorry, you can plug it into the equation now. So for my t-test, I first have to start with x bar 1 minus x bar 2 minus the population mean minus the population mean, but again we're claiming that they are equal, so their difference is going to be 0. So I'm going through and I'm using the equations where my variance is not equal. So my denominator is going to look like this, over n1 plus squared over n2. So now I just take it to my calculator and I'm plugging everything in. Okay, looking at that, that is not in my rejection region. So I would say fail to reject. So if I'm not throwing it out, I'm not supporting the claim. So I could say at 10%, I am not supporting the claim. The manufacturer claims the mean calling range in feet is 2.4 for cordless telephones is greater than that of its leading competitor. You perform a study using 14 randomly selected phones from the manufacturer and 16 randomly selected from its competitor. The results are shown at the left. At a level of significance of 0.05, can you support the claim? So first of all, the claim is the mean calling range of the manufacturer's cordless phones is greater than the leading competitor. So start out with your H sub O and your H sub A is greater than your leading competitor. This would be my claim. Okay, so looking at that, I know that I have something that's right-tailed. Okay, and my level of significance is 0.05. So because the variances are equal, it says assume the populations are normally distributed and the population variances are equal. That means my degree of freedom is going to be N1 plus N2 minus 2. So I'm looking at a degree of freedom of 28, a level of significance of 0.05. I'm using the T-chart, so I'm looking at one tail, and it's going to be positive because I know it's right-tailed, and I see it is 1.701. So now it's time to go and plug into my equation. Remember, this one is way more complicated than the equation for things that are equal. So my standard error equation, I first have to find the pool estimate. So N1 minus 1, 14 minus 1 is 13, times my standard deviation squared, plus N2, which is 16, minus 1, times my standard deviation squared, all over N1 plus N2 minus 1, which was my degree of freedom. And I have to multiply that by 1 over N1 plus 1 over N2. So plug that all into your calculator. Okay, so now you go and you plug it into your t equation, which would be x bar 1 minus x bar 2, always assuming the difference is 0 between the populations, divided by my standard error. So looking at this, this is in my rejection region, so I would reject H sub O, which means if I'm throwing that out, I am supporting the claim. Alright, so we will start the assignment together